Monday to Friday.
From 9 a.m.
This is Views and News with Clarence Ford.
Only on Cape Talk.
It's 9:37. It's Friday, and after 9:30 on a Friday, we chat with Dr. Chris Smith, lecturer at the University of Cambridge, the Naked Scientist. Our Naked Scientist, an opportunity for you to have your questions answered. And you're welcome to register your questions via WhatsApp on 072 567 1567. You can call. We'll prioritize that call on 021 446 0567. Welcome, Dr. Chris Smith. Great to have you back.
Good morning, Clarence.
And maybe an opportunity to check in on the weather. It was miserably, well, you were expecting a bit of a heat wave last week, wasn't it?
Well, the weekend was wonderful. It was about 20 degrees, which is unseasonable. And then it forgot that it was having a heat wave and we relapsed back to normal temperatures. And it's raining today. You'll be reassured to know it's raining and it's cold and it's miserable. So no vitamin D for me today.
Just to understand, so 20 degrees is a heat wave for you?
Well, this time of year it is, yeah. I mean, remember 2 years ago, we had the hottest summer we've ever had, and one of the days it was 41 actually, and that was a record for the UK and that time of year. This time of year, it is actually supposed to be pretty cold and miserable, but we just forget that, and we always look with rose-tinted spectacles. That's how memory works. We always dwell on the good times, which is probably a devolved trait. And so we tend to think it was nicer in the past than it really was. So I think we're probably sort of par for the course, to be perfectly honest.
And your days are getting longer. So let's get to the questions. A question in about the eclipse that we've just witnessed, or some of us witnessed. We saw recordings thereof. The question is from Melvin. Is it just a fantastic coincidence that the moon is just the right size for a total eclipse?
Yes. And the reason that it is because the moon is moving, not just across the sky, because the Earth rotates inside the orbit of the moon, and this means the moon rises and falls, a bit like the sun does, but the moon is also moving farther away from the Earth. And this is because as the Earth turns, the moon attracts water on the Earth's surface closest to it. It also causes a bulge on the other side of the Earth for another reason. And this has the effect of slowing down the Earth a bit by exerting drag and giving some of the Earth's spin energy, some angular momentum to the moon. And that has the effect of pushing the moon slightly farther away from the Earth every year. So its distance between us and it is growing by about 2 centimetres every year. We know this. It's been accurately measured because the Apollo teams left a mirror on the moon's surface and a laser beam is bounced off that mirror. And because we know how fast light travels at the speed of light, 300,000 kilometres a second, you can work out how far away the moon is extremely accurately. And that's why we know the moon is moving farther from us. So when the moon first formed about 4.5 billion years ago, it was much closer in. It would have driven enormous tides, and it also meant the day length was shorter. The moon has moved farther away, the Earth has lost spin energy, it's slowed down, days are longer, but it's put the moon into a position where just by chance the outline of the moon now matches the outline of the sun, pretty much 100% give or take. And so we have these very nice eclipses that you can witness at certain places at certain times, the way we did last week.
Let's go to Nicolette. She's on the line from Constantia. Welcome, Nicolette. Go ahead.
Good morning, Dr. Chris and Clarence. I'd like to find out whether past life is actually acknowledged. I have a granddaughter who actually talks about how she died in a past life.
Woo!
And she has these like nightmares that have gone on. She's now 10 years old. And it's quite horrific what she says happened to her. And she's not outgrown it. So I just wanted your take on this, please.
Good morning. Well, the bottom line is that everyone dreams and everyone has nightmares, and they are most common in young people. So it's not unusual to have nightmares. Children begin to dream the way we think we dream as adults by the age of about 5. It's surprising, that statistic, isn't it? And the reason is thought to be that the brain matures to the extent that you can begin to envisage in 3 dimensions in your mind. If you can take a picture of something and then build it with building blocks in your mind's eye, then you can dream. And that normally happens by about age 4 to 5. And nightmares seem to dominate. Now, we don't know why. Neuroscientists don't know why nightmares dominate. And we also don't know why certain characteristic nightmares tend to dominate, but they're very, very reproducible. If you go around the world to different cultures, people speaking different languages, people with very different upbringings, there is a strong consistency in the sorts of things that people go through in their dreams and nightmares. And most dreams are nightmares. Actually, most people don't dream really nice stuff. They tend to dream horrible stuff. And they're all involving threat or pursuit. And one theory is that perhaps this is the brain mentally rehearsing ways in which, if the worst were to happen, what we would do about it and how we would cope. So it's a way of letting your imagination run with a free rein over things that we might struggle to cope with or find difficult during our waking hours. It's just a theory, of course. Now, in terms of where these dreams come from, this is generated by a range of different things. We know that your day-to-day experience can influence the pattern of your dreams, because people will say if they do a lot of something or they're involved in something during the day and they're doing it a lot, it then tends to crop up in dreams and nightmares a lot. So the brain is basically replaying experiences of our day-to-day living, things we've seen, things we've read, things we've heard, but also things it can make up. But it doesn't make up things that are so weird that they just don't exist in reality. So in other words, it must be informed by our experiences to at least some extent. Now, where those experiences come from, it's certain that the brain is generating a lot of this activity spontaneously. We're not writing specific memories of our events into a way that could be heritable. We're not, for instance, writing a DNA message about what I did yesterday and then putting that in a form that I could pass on to my children. We don't think that's happening. Some sorts of learned, or so some sorts of heritable behaviours are passed on genetically. Birds know, in inverted commas, how to build nests. Animals know when to mate, when to hibernate, when to migrate. For example, this must be genetic. So there are some behaviours that are written in that way, but we don't think what we call autobiographical memory is written in that way. So we don't think that is heritable. So I think in this circumstance, this is almost certainly normal development. It's probably informed by day-to-day experiences and normal childhood fears that are then built by the brain into some kind of coherent story that the brain then embellishes a bit in order to make sense of it. But I don't think it's anything more than that.
Obviously, the threat of war looming large. Probably the reason for this question, is it possible to launch intercontinental ballistic missiles that are not detected by satellites?
Very difficult to do anything these days that someone doesn't know about. If you launch something, you make vibrations on the ground, which can be picked up by really sensitive instruments. You usually launch them using systems that produce a lot of heat because of the way in which they are propelled, and that can be picked up both from the ground but also usually from space. There are satellites with heat signature detection built into them. You can also then track movements. We've got satellites using radar. They do this ostensibly, for instance, to look at the surface of the sea to measure the heights of waves and so on. Yes, you can measure ocean height and wave height from space, and scientists are doing that. And this means you can easily see things that are going where they shouldn't go, which have a very different signature that stands out from the background. So my argument would be it's very, very difficult to do things these days at the sort of scale that would unleash any kind of devastation that someone somewhere doesn't continuously know about.
Then we have a question in. Hi, Dr. Smith. Which animals have the best memories? We all know elephants are supposed to, but is this proven? Solly, with that question.
Hi, Solly. I think, well, my money would probably go on something like jays, scrub jays, members of the crow family. These have a exceptional cognition and an amazing memory. And the reason they have an amazing memory is they hide stuff. And they hide stuff not just so that other things won't find it, but other members of their own species won't find food. Because what they do is as soon as they get a choice morsel, they'll go somewhere, look around furtively to see if anyone's watching them. And if no one is watching them, then they bury the food or hide the food. And they remember where. and they come back and get it later. And they can have enormous numbers of food items concealed in this way. And they do it because they know that they can plan for the future. They know that today is a good day, but tomorrow might not be. And so they put all these food caches in places they can remember so that they can go back and retrieve them later when they're hungry. So those would probably be at the top of my list. We know other animals. You mentioned elephants. Yes, they have incredibly good migratory maps. They remember their way around over vast distances and can integrate enormous numbers of cues in order to find their way from A to B over massive, massive distances and long durations and for long periods of time. And probably the poor reputation in the room is held by the goldfish, where people knock fish for having a 5-second memory. It makes one lap of its bowl and then it's forgotten. But actually, that's not true. And there was a guy in Australia called Cullen Brown about 20 years ago who did some lovely experiments where they showed that fish have an excellent memory. And he trained some fish in a tank to find a hole in a fishing net so they could escape, and then put them away for a year or so, just fed them, let them go about their fishy business, came back a year later, retested them, and a very significant proportion remembered from a year ago what he'd taught them about how you escape from the fishing net, given a certain cue. So fish also have a bad rep, which is undeserved. They also have very good memories.
Okay. And then we have another animal-related question. Or is it really? No, it's not. Clarence, Dr. Smith, just heard Dr. Smith talk about animal instincts like birds knowing how to build nests. Do humans have any natural instincts? Marty in Sea Point.
Oh, yes, absolutely. And in the same way as if you watch a chimpanzee, I know chimpanzees are not human, but they're very closely related to us. We think they're about 1 or so steps away on the evolutionary tree from us. So they're a good model for where we came from and also how we tend to think and innate abilities we have. Chimpanzees that have never seen snakes are absolutely terrified of snakes. They're very cautious around snakes. We have certain innate things that we tend to find repugnant. We stay away from things that are rotten or smelly or disgusting. We've learned that probably if we were to go near those, they may pose a threat to our health, so we avoid them. There are things like spiders that we find scary, and so we stay away from those. We're frightened of falling off of a height. If you're a young babies are often quite, I would say that they're not frightened at all by a height. You can push a baby onto a sheet of glass over what looks like a drop, and the baby will crawl across it no problem. But take a toddler, and they'll very quickly say, I'm not going to do that. So we have wired into us ways, once we become capable of doing ourselves harm, ways of avoiding bad stuff. Now, no one teaches these individuals these things. It comes naturally. So in other words, the brain obviously inherits a set of instructions to wire itself up in such a way that once we become competent and capable of doing things, there are things we absolutely don't do because we know they're probably going to do us harm. So yes, there are many behaviours that we just do naturally and come instinctively, and most animals have this to some extent.
We're chatting with a naked scientist, a regular appointment on a Friday, an opportunity for you to ask your question, a question about gravity. Can gravity, Corey with this question, can gravity be 1g on a planet with a much greater mass than Earth?
Yes, it can. And the reason for this is that gravity acts through the centre of mass of an entity. So gravity is operating through the centre of the Earth, 6,000 kilometres beneath our feet. And the way we feel gravity is that it's a function of the mass of the Earth and the distance away from the centre of the mass. So if you have something which has a much greater mass than Earth, but also a greater size than the Earth, and you get the proportions right, you could end up with something which is much bigger than Earth, but has the same gravity. So Jupiter, for example, you could pack the Earth inside Jupiter about 1,000 times. It's absolutely huge. But the gravitational attraction at the surface of Jupiter, because of the size of Jupiter, is only about 2.5 times greater than on the surface of the Earth. Bit surprising that, isn't it?
Okay, so you're saying it's volume, it's not mass-based gravity.
No, gravity is absolutely proportional to mass. But the distance away from the centre of the mass is also important because gravity obeys what we call an inverse square law. So if you double the distance from A to B, then you actually get 1/2 squared, a quarter of the gravitational force that you feel when you double the distance, because it's an inverse square law. So if you go to something which is twice the size of something else, the gravitational force would be a quarter. of what you were
Ding
feeling.
dong.
But if you increase the mass proportionally, so say I've got something with a different density to the Earth, so the size is bigger but the density is different, you can have the right relationship, so it's the right size, so even though the distance has got bigger and the gravity's got less, it could potentially have the same gravity as on Earth.
A ding dong moment for me. Another, let's stay in space. If we can't terraform Mars, then where's humanity supposed to go when the Earth becomes uninhabitable or when the sun turns into a red giant, possibly swallowing us?
Well, that's why we have to look after the planet we have got, because we haven't got a planet B. Ba-boom. There is no, at the moment, other option. Anywhere we go is not going to be a home from home for us. Certainly not with the technology we have at the moment. Maybe in the future we'll be able to do that. But it's a reasonable point that one day the sun, as it ages, it's about halfway through its life at the moment, and it's burning through its hydrogen fuel, and it's getting hotter, and it's also swelling up. And it will get to a point in about 4 billion years' time where it swells up to such a giant size as it gets hotter and hotter and pushes itself outwards that it will completely eclipse not just Mercury, not just Venus, not just the Earth, but Mars as well. The sun will stretch all the way from where it is now out to beyond the orbit of Mars and consume all of the inner rocky worlds. What a bleak thought. That means we do have, in about 4 billion years' time, a problem to solve. Hopefully, by then, though, our technology will have advanced a bit further than it is today, and we will have options for how we do go to somewhere else. Now, whether that means we by then have conquered space and time, it's not a problem and we can just find ourselves a new home, or whether we have become so advanced that we build these amazing floating planets of our own in space that we can propel around the solar system and beyond. Who knows? But we've got a few billion years before we have to worry about that. We've probably got more acute crises to deal with in the short term, like climate change.
And I'm going to be 4,057,000,000 years old. How old are you going to be when that sun becomes a big giant? For some reason or the other, we want to stay in the universe this afternoon. The question from Nitin, what was there before the beginning of the universe? Does time also really start? I mean to say how it is like without time. Can there be a situation where time does not exist at all?
Well, if you ask a philosopher what's outside the universe, they'll say nothing, because by definition, the definition of the universe is everything. Therefore, when the universe didn't exist, nothing existed. Difficult, circuitous argument, because, of course, what's the universe growing into? Where did it come from? What's its origin? We have no idea. There's clearly a lot more physics that we have yet to learn, but what we do know, we can put a pretty accurate date on the origin of the universe. It's been dated via a number of mechanisms and methods, and we know the universe is about 13.8 billion years old. That's the point when this posited enormous catastrophic explosion, the Big Bang, went off and transformed something which was infinitesimally small but energetic into the enormous entity that it quickly became, with a period of very rapid growth, then slower growth that's slowly speeding up again to give us the universe we have today. Time started ticking for our clocks in this universe 13.8 billion years ago. But what happened before that? We have absolutely no idea.
So did the Big Bang happen anywhere or everywhere?
The Big Bang effectively happened everywhere, because there was nothing before the universe popped into existence with the Big Bang for us in this universe. And many people say, well, what I don't understand is there's this thing called the cosmic microwave background radiation, the afterglow of the Big Bang. And if I'm sitting here on Earth and I look in any direction in space, I can see this radiation, this microwave radiation coming in from space, which has got the fingerprints of the Big Bang written all over it. But it's coming equally from all directions. Now, the Earth isn't at the centre of the universe, so why am I seeing this equally in all directions? And the reason for this is, given that the universe is older than our solar system, and the reason for this is that when the universe first formed, the material that was formed from the Big Bang shared the energy of the Big Bang equally among all that material, and then this process of very rapid inflation occurred, which blew the universe up into an enormously big entity that it became, separating all of that material all over the place equally, so that because that energy is distributed equally and in a smooth, homogeneous way across this early universe, when we then see that material coalesce into galaxies and then stars and planets and so on, you look in any direction and you see that energy being radiated at you equally from all directions, because in theory, effectively, we were at the centre of the universe because everything was at the centre of the universe when it first formed, but then it's inflated and changed and evolved since that time.
We thank you, Dr. Chris Smith, lecturer at the University of Cambridge, the Naked Scientist, and of course a regular date, 9:30 every Friday. And all of that brings the time to 10 o'clock exactly. Time for Eyewitness News at this hour. Natalie Malcha standing by.